Hi everyone, I'm Lisa, and today I would like to introduce you to our work, Blockchains Enable Non-Interactive MPC. This is a joint work with Vipul Goyal, Brian Pano, and Ifan Song. And this is also in the fulfillment of my speaking skills requirement. If at any point in time you have questions about the talk, or if anything is unreadable, or if you cannot see something on the slides, please just let me know. And the same is for the people who are on Zoom. Okay, so let's dive right in. Before we start, I would like to explain to you what this obscure MPC acronym, which we use in our title, means. It stands for Secure Multi-Party Computation, and is actually a quite useful cryptographic primitive. So, for example, you can imagine that my 3 co-authors and I have finally managed to get this paper accepted, and we are now trying to figure out who will be the first author on the paper. So the conference does not provide any sort of guidance on this, but everyone knows that it is great to be the first author. However, like every one of us has each preference, right? So every one of us has some idea of who should be the first author, but we don't really want to hurt each other's feelings, and so we don't want to disclose our preferences. Also, unfortunately, our Brian here is clearly malicious, and he is trying to trick everyone into choosing him to be the first author, which clearly does not help us. And MPC can help in this situation. So MPC will allow mutually distrusting parties to compute an outcome of the function on their private inputs, while ensuring that nothing besides this output is leaked. And this guarantee should hold even if some of the parties are malicious or adversarial. And in this particular work, we will consider a very strong kind of malicious behavior. We will consider so-called fully malicious adversaries. So what it means is that the parties can deviate arbitrarily from the protocol description. So for example, the parties can arbitrarily quit the computation, or the parties can skip some messages that they're required to send according to the protocol, or the parties can be extra sneaky and send the wrong messages. So for example, if according to the protocol, a party is required to send some message x to the power of 2, then the party could actually send some message x plus 1 to the power of 4. And the goal of such adversaries is typically either to learn some non-trivial information about the inputs of the honest parties, or to somehow bias the outcome of the function in a way that they are not supposed to. And even though this adversarial behavior seems like very strong and very hard to sort of handle, there are MPC protocols which can handle such adversaries. And I guess it's not very surprising given that MPC has been around for a very long time. So this cryptographic primitive has been introduced in the 80s. And since then, there has been a lot of research on MPC, and in particular, a lot of research focusing on the communication complexity of MPC and the round complexity. I'm not quite sure if everyone is familiar with the notion of round complexity, but basically, MPC protocols run for multiple rounds, and ideally, we would like to have as little as minimal rounds as possible. And now we know that under standard assumptions, such as, for example, the hardness of discrete log or the hardness of factorization, 4 rounds will be necessary and sufficient for MPC in the fully malicious case. This is great. So is MPC solved? Unfortunately, the answer is no. So typically, MPC requires synchronous communication from the participants, and the participants are required to interact with each other for multiple rounds. So how a typical MPC protocol works is that I compute my very first message based on my secret input and maybe some randomness, and send it to my 3 co-authors, Brian, Ifan, and Vipul. And then Brian, Ifan, and Vipul do the same. So they somehow also compute the very first message according to the MPC protocol and send it to everyone else. Then I will gather these messages and combine it again with my sort of secret input, my randomness, and produce the second message of the protocol. And this interaction is run for multiple rounds. And even though the adversarial parties may not respond, or they may drop out of the computation and so on. The assumption is that the honest parties are sort of online and participating during this whole round of the MPC protocol, and they are able to respond to the queries online. Why is this a problem? Well, think, for example, that we now have not only me and my three bosses, and we are trying to figure out who will be the first author on our paper, but rather that we have all citizens of the US who are trying to figure out who will be the next president of the US. In this case, it would be sort of somewhat silly to assume that millions of US citizens will be online at the same time and participating in this interactive MPC protocol for multiple rounds, right? So this seems like a very, very problematic assumption. And so motivated by this problem, we asked ourselves the following question. Can we come up with an MPC protocol which does not require parties to be online at the same time, and also requires only one round of participation from the parties who supply inputs, but are maybe not interested in contributing to compute the output? They might be not that interested in learning the output. And we would like to answer this question while assuming that all but one of the parties are fully malicious. And in this work, we are able to answer this question positively. And in the next 30-40 minutes, I will hopefully explain to you how we are able to do it. So let me briefly talk about the structure of the talk. In the beginning, I will introduce to you our setting and the assumptions that we make. Then I will talk about the background and main ideas of our paper. And we will then discuss the challenges that we encountered and the solutions that we came up with in order to solve these challenges. Finally, we will briefly talk about the related work. And then, this is really, if we have time, I'm not quite sure, probably not, but if you're interested, there are also some variations of our construction. If we have time, then I will mention those. Okay, so as promised, let us briefly talk about the setting and the assumptions that we make. First of all, we assume the existence of a cryptographic primitive, which is called public bulletin boards. And what the public bulletin board does is, well, you can imagine it as being an append-only log, where the data can be published, and the published data cannot be erased or modified in any way. So for example, if Ifan and me go ahead and publish some data, we can do that. And then even if some malicious Brian comes along and tries to, change our data or, swap our data with his data, then Brian cannot do that. And furthermore, we assume something which we assume that once the data is published, the party gets sort of a receipt of the fact that this is exactly the data that this party published. So we will call this receipt a proof of publish or proof of publication. And it is quite exciting that actually multiple works pointed out that instantiations of such a primitive do exist in real life. And the most notable example is blockchains. Okay, this is great, but we will need something more. So we also need a primitive which we call conditional storage and retrieval systems. And you can imagine a conditional storage and retrieval system as sort of a black box where you can store a secret and specify a release condition. The release condition can be any empty statement. Then if someone knows the witness for the statement, this party can retrieve the secret. To give you an example, let's say we have Weeple, and Weeple wants to reward someone who is able to solve homework 5. Right, so Weeple will store his secret with the CSaR and specify the homework 5 as being the release condition to be able to obtain the secret. Ifan, being the smart student that he is, actually solved homework 5, so he knows the solution. And he is now able to use the solution to obtain Weeple's secret. And this all can sort of happen while Brian is watching vpools and events interaction, but Brian does not know the solution to homework 5, so Brian does not get any information about the secret. And in fact, there were a few works which proposed similar functionalities. And in this work, we were able to prove that one of these proposals actually satisfies our definition for security for CSaR. And what is even more exciting is that both bulletin boards and CSaRs can in fact be instantiated via blockchains. And so this is why we will say that we work in the blockchain setting.
I guess I didn't quite get how you model blockchain. How should I think of blockchain?
So, I mean, we don't like blockchain is really only the instantiations. So we will only talk about the public bulletin board and the CSaR. So we only mentioned blockchains. So we only mentioned that, we work in the blockchain setting because both CSaRs and public bulletin boards can be instantiating using it.
So I guess you are saying the CSaR instantiated from blockchain is described in the previous paper.
Yes, exactly.
But,
so
I guess maybe my question in the previous paper, what's the model for blockchain?
So in the previous paper, what we did is we had the committees of miners. And we were secret sharing the secret to each miner in this committee. And the committees were chosen in a way that basically these were the n last people who mined the block on the blockchain.
Yeah, I guess I'm kind of confused about the model. Because like in the theorem statement you use that you have a blockchain model, so it's like I feel like it's important to understand what blockchain model means.
So I mean, you can think of it as, this is just really a shortcut. So we assume the public bulletin boards here and the CSaRs. This is all you need for this work. And like you can think that in practice, you can use blockchains to achieve both of them. So we will not go into the details of how blockchain works or anything else. This is
bulletin board is just like a broadcast channel. No different from broadcast.
This is slightly different from broadcast, I guess. In the sense that, for the CSaR, you will need someone to privately store a secret, right? For a while, and then we will pass the secret to some other set of parties, which will be.
No, but I'm asking about the bulletin board.
Oh, for the bulletin board, yeah.
That just means broadcast.
Yeah.
Okay.
That you cannot that is like everlasting, right? So you cannot change it later on. Yeah. Okay. And the final sort of important bit in our setting is that we distinguish between two different kinds of MPC participants. So we will have contributors. These are the parties who supply inputs. So my 3 co-authors and I in our very first example. And we will have the evaluators. This will be the parties who will execute the computation. And these are the parties who are interested in learning the result. And know that some parties, these sets can be, overlapping, but this is not a requirement. So in fact, there can also be a single evaluator who maybe did not supply any inputs. This is also possible. Okay, and what we are trying to achieve is we are trying to obtain MPC, which does not require interaction between the participants and requires only a single round of interaction from the parties who supply inputs but are not interested in learning the output. So to put it into some context, when we have traditional MPC, you have the situation on the left, right, where we have 4 different parties and they're participating with each other over multiple rounds. And now we want to achieve something that is more similar to this picture on the right, where each party somehow takes the data that will be needed for the computation, just drops this package off somewhere, and then the evaluators will come in, take these packages, and maybe take them sort of round by round somehow, so the evaluators can participate in multiple rounds. But the evaluators will take these packages, perform the computation on behalf of the contributors, and output the this function that we wanted to compute.
So does being an evaluator mean that, I guess you mentioned people who are not interested in learning the output. Does being an evaluator mean that you're interested in
Yes.
learning the output?
Yep.
Are those exactly the
Yep.
same or?
So one interesting thing is that here, like the evaluator can actually, like in this work, the evaluator can actually contribute to the evaluation, but maybe not for the full time. And so the evaluator will have to like figure out the result, but maybe if he's not super interested, then he will not go along the way like fully. So if you are interested to learn the result, then you can perform the computation fully. If not, if you're just interested in helping out with learning who will be the next president of the US, then you can help out a little bit. Okay, and in fact, what we will be able to achieve is not only sort of a single construction, which corresponds to this picture on the right that I just showed you, but rather we will provide a transformation, which can take in any interactive and possibly multi-round MPC protocol and transform it into another MPC protocol, which now does not require interaction between the participants and is only single round for the parties who supply inputs but are not interested in the output. If the original protocol is secure against fully malicious adversaries, so remember these were the ones who can just deviate however they want, then the new protocol is also secure against fully malicious adversaries. And if in the original protocol we are allowed up to T out of N parties to be malicious, then in the new protocol we allow up to T out of N contributors to be malicious. So this translates 1-to-1 essentially. And we also have the evaluators in the new protocol, and in fact we allow even for all of the evaluators to be malicious. Yep.
What if all the evaluators are malicious? Like then they can just dictate the outcome.
They can dictate the outcome. So like then you lose the guarantee on like the outcome being computed correctly, but you still have the guarantee that the security of the inputs has been preserved. So if a party is malicious, then we don't really care about what sort of guarantee this party has. So like we don't provide any security guarantees for the malicious parties. We don't guarantee that they will get the right output if they're misbehaving.
Do you guarantee something of the form like if some evaluators are honest, then you'll get the right output, or not even that?
This is a good question. In one of the variations of our work, we do guarantee that. We do guarantee that they will get the output. I will not talk about this one, but if you're interested, you can ask me later about it. If not, then we will guarantee that no honest evaluator will be sort of convinced in the output. So.
How many rounds of communication do the evaluators do?
Essentially, approximately how many as many as is done in the original protocol. So like if you're plugging in like a protocol with 4 rounds, then this is approximately how many rounds.
So the evaluators, can I think of them as using like a prior
like is
using the inputs just from the motion.
Yeah. Okay. So one more time, just to make sure that everyone does understand this. So we will start with an original MPC protocol, which is interactive and multiple rounds, and allows us to figure out who will be the first order of our data securely. And maybe do some other cool things. And we will take this MPC protocol and transform into one that is that does not require interaction between the participants and is only single round for the parties who are not interested in the output. And this protocol will as well allow us to figure out who should be the first author on our paper. And to give you an idea of how such scheme could work, like how such transformation could work, think about the first round of this MPC protocol on the left-hand side, right? So for the first round, there was no interaction before, so the only thing that you can do is you can somehow compute the first round of the first MPC message based on your own input and some randomness. And then according to the MPC protocol, I will send it to Brian, Ethan, and Default. So what I could do instead is I could instead take this message and simply publish it on the bulletin board. And then everyone else could do the same thing with their own first messages. And now, instead of talking to each one random people, I could just take a look at the bulletin board and read their messages from the bulletin board and use these messages in combination with my own input to compute the second message of the MPC.
If we're going to use the bulletin board to implement point-to-point communication, you just use like public key encryption, right? Oh.
So if you need to go from if you have like some secure point-to-point channels, then you need to like some encryption silent messages.
Right.
But, yeah. Okay, so here we already sort of removed like a little bit at least the interaction between the participants, but we still need the parties to participate for multiple rounds, right? And the reason is that the parties, like to compute the output of the second round of the MPC, the parties need their own like sort of secret input in combination with these messages that were published on the bulletin board. And so if you could somehow encode this computation securely, that would be great. And so to talk about it in a more formal manner, I guess I would like to introduce the following notation. So when you think about a protocol, so not really only MPC, it can be any protocol, you can think of it as being defined by a set of functions which determine the behavior of each party I for each round J. Right, so these are the functions which are called next message functions, typically. And what they do is they just take the input of the party, the randomness that the party is using in this round, the messages that this party received in the previous round, and the state that this party passed from the previous round. And we just figure out what message this party should send in this round and what is the updated state. This is already stated. Is this clear? And so using this notation, the protocol is actually quite simple. So starting with the original interactive multi-round MPC protocol, each contributor does the following. Each contributor will sort of cleverly encrypt the next message function for each round while hard coding their private inputs. And then these sort of encrypted circuits, encrypted functions, which will be stored with the CSaR, which provides us with a secure storage solution. And what the evaluators will then do, the evaluators will just retrieve all the encrypted circuits and execute them. To sort of elaborate on this idea a little bit more, think, for example, of, let's say we had like some MPC protocol which has two rounds. Let's say about it for a second. So what happens is the parties can still first publish their first messages on the bulletin board. Right, publishing these messages is fine because these are the messages that come from the MPC protocol, so they are secure. But instead of sort of waiting to see what the other parties publish on the bulletin board in order to figure out the second message, what we are now doing is we are now encoding the computation which is done by the next message function of the second round for this particular party, while hard coding the private input of this party. And we store these sort of like encodings of the computation with the CSaR. And now what the evaluator will do, the evaluator will first get read the information on the bulletin board. So the evaluator will get the messages of the first round. And the evaluator gets the encodings from the CSaR for the second round. And then the evaluator just, for example, gets the encoding of my own next message function for the second round and executes this encoding on the messages that were published by Brian, Ethan, in the very first round. And so this will give him the message that I would output in the second round. And the same is done for every single party. So essentially, the evaluator is performing the exact computation of the original MPC protocol on behalf of the contributors.
What's the release condition here?
What's the release? Oh, this is a great question. We will talk about it a little bit later. The release condition will actually be dependent on the messages that are published on the bulletin board. Yeah, so you're not allowed to get all of the information. You will be allowed to only get some of the information, which is why we actually use the CSaRs. Yeah.
And also how to encrypt the circuit to protect the.
Yeah. Also a great question. So what is this clever computation encoding that I'm talking about? So essentially, we are using something which is called a Yalom's goblet circuits, which is not a new idea. It has been also introduced in the 80s. And I don't have time to make a full introduction. I do have a backup slide if someone would like to know a little bit more. But essentially, what you do is you represent your function as a circuit. And then you sort of perform the encryption of the circuit gate by gate. And decrypting one gate will allow you to partially decrypt the gate that is connected to this one, right? So each gate will have like two inputs, which probably come from some other gates. And once you decrypted the first two gates, you will be allowed to decrypt their sort of like child gate. The important thing is that the intermediate results are hidden, and that you need to somehow obtain this sort of initial varieties for the gates that are on the very first level that are not connected to any other gates. And this is like how you sort of get input into a goblet circuit. So depending on your input, you will be able to sort of get one set of keys, but not the other set of keys. So in a little bit more detail, for each sort of input wire, there will be one key which will correspond to this input wire being bit 0, and one which will correspond to this wire being input 1. And then depending on your input, you would want to obtain either the key for 0 or the key for 1. The sort of important thing for us to keep in mind is that the goblet circuits are secure only if a single key is revealed for each wire. So you can never reveal both keys. This somehow makes sense, hopefully. And typically in Yale's goblet circuit construction, there is this separate step where the party is obtaining the correct input via keys. And this is done by a cryptographic primitive, which is called oblivious transfer. And what you get with oblivious transfer is essentially if I, for example, have two keys and n here has bit 0, then n will be able to obtain my key for the bit 0, but there's no information about the other key. At the same time, I will not learn whether n actually chose 1 or 0. The issue with this is that this is an interactive protocol, and we're trying to provide a non-interactive solution. And this is where we use CSaRs. So the wire keys will actually be stored with CSaRs, and we will design some clever decryption conditions to make sure that only the right keys are revealed. Okay, so like this is the final sort of big picture of our construction. We will use the interactive multi-round MPC protocol as the starting point. The contributors will garble the next message functions for each round and hardcode their private inputs. And then the garbled circuits and the wire keys for the garbled circuits will be stored with the CSaR. And the evaluators then retrieve the garbled circuits and the wire keys, or like a subset of wire keys, from the CSaR and execute the circuits. However, the non-interactive setting is actually pretty hard. So, for example, you can think of, let's say that in the interactive setting, I'm interacting with Abhiram, and Abhiram is, trying to convince me to for example, execute the 5th round of the MPC protocol, and I know that I am on round 3, then, I will probably just politely refuse and say, okay, let's execute round 3, let's execute round 4, and then I will execute round 5. But now, once the evaluator obtain the garbled circuits, they can just execute, like, they can do this, the garbled circuits, whatever they want, essentially. So they could execute the garbled circuit for round 5, they could then execute round circuit for round 4, and so on. And so, as we want to make sure that, we do not leak any more information in our new construction than, what is leaked in the original MPC protocol, this is something that we need to prevent. So this hopefully gave you like a general idea of what we will try to accomplish. And I will now go into a little bit more detail on sort of a few of the problems that we had to solve because of this. So one problem that I already mentioned was that we in fact need to ensure that for each input via of each garbled circuit, only a single wire key can be revealed, right? This was related to the security guarantee that we had for the garbled circuit. However, the inputs of the other parties are unknown at the time when we store the garbled circuits and when we store the wire keys. So essentially, we somehow need to ensure that the evaluator is able to obtain the wire key that he needs while ensuring that the evaluator is only obtaining a single wire key and not both. And how we do it is we actually require the evaluator to commit to the execution on the bulletin board. So once the evaluator is done with figuring out the output of some round I of the protocol, the evaluator will just take the output of these like garbled circuits for round I, concatenate them, and post this message MI on the bulletin board. And the garbled circuits and keys of round I+1 are released only after this message is posted. And for this, we will use CSaR in combination with this sort of proof of publish that the public bulletin board provided us. So the evaluator will use the proof of publication of this message MI as sort of the witness for the release condition in the CSaR. And we will also store both wire keys with the CSaR, but we will store them in 2 separate CSaR requests, which will have 2 different release conditions. And specifically, in order to release the key, which corresponds to some wire X having bit B, we will check whether the proof of publication of this message MI contains exactly the B on position X. So this is how the evaluator will ensure that he is getting the right piece, but only a single one.
I'm still confused about in normal garbled circuit protocol for both parties who learn about the final output, there will be a final round of communication that the evaluators send back the output label to the gobbler, right?
So I think you can probably skip that. You can probably also output the like in the very, very final round. I think you can also output the result of the computation itself, right? Like instead of encoding the key, you could also encode the value itself.
Oh.
In the very final one.
What is M?
What kind of guess? So if let's say the evaluator is computing, like wants to get the garbled circuits for round I+1, right? For this, we require the evaluator to commit to the input of these garbled circuits, which will be the output of the garbled circuits of round I. And so this message MI is exactly the output of the garbled circuits of round I, meaning that this is exactly the message that was broadcast in the original MPC protocol in round I.
So it contains message from like everyone though.
Yeah, everyone. You can just concatenate them and this will be the result.
What does it mean release condition for bit be on wire X? I thought you are releasing the Gabble circuit for the next step.
I'm releasing Gabble circuits and I'm releasing divide keys. You need both, right? So like you separately need the Gabble circuits, which will just be a bunch of encrypted ciphertexts. And you also need divide keys for the initial wires. And in order to obtain the wire key which corresponds to the input that the Gabble circuit needs, this is exactly, which will be exactly this message MI. I require the evaluator to commit to this message MI on the public bulletin board.
So MI is like encoding. MI is that the Gabble encoding of the Gabble?
No, MI is the output.
It's a clear text output.
It's a clear text output, which is exactly the like the messages that the parties in the original BC protocol will send to each other in round I. Because these are exactly the inputs that you would need in the next message function of the next round, right? So you just need to take a look at whatever messages were published in the previous round, combine them with your own input, which is hard-coded in the Gabble circuits, and this is how you proceed in the computation. And we just need to make sure that the evaluator can never sort of run the Gabble circuits on different inputs multiple times.
So if the evaluator modifies the it will not be
No. This is exactly the same as having some party misbehaving in the original protocol. And in fact, maybe like one more thing to make it even more clear, I do not talk about this in this talk, but we slightly modified the original MPC protocol so that we ensure that all messages are signed by the parties. And so you will actually have the signed messages in MI, and you will, in the Gabble circuit, you will also check whether all the signatures check out.
So is there an evaluator that acts on behalf of each original party?
Evaluator can act on behalf of each party. So they can be like a single evaluator, that's fine.
So that then it can corrupt all parties in the original.
Then it can corrupt all parties in the original protocol. The evaluator will not get any sort of reasonable response out of this. So essentially,
The original protocol, you need some guarantee of the original protocol when all parties are corrupt.
not all, like all but one.
If the evaluator is malicious and it's acting on behalf of all parties in the original.
So this will be fine. So as I said, we will slightly modify our construction so that the honest Gabble circuits check whether the signatures, which are used in combination with the messages from the previous round, whether all of those signatures check out. So if the evaluator is malicious, then the evaluator will still not be able to forge a signature of some, honest party from the original MPC protocol.
You are assuming the output from the original MPC protocol is signed.
Yeah.
That's it.
So I'm not talking about this here, but this is exactly what helps to solve your issue. Okay, so the next issue that we had is that, as I mentioned, for example, there is some issue with the input consistency. So let's say in the original MPC protocol, I'm broadcasting the messages, and Repo is broadcasting message M, and Brian and Ethan are always able to see that this was exactly the message that was broadcast by Repo, right? So there's no way that Brian thinks that the broadcasted message was M1 and Ethan thinks that broadcasted message was M2. And the broadcasted messages are exactly the inputs to the Gabble circuits. The issue now is that Gabble circuits are sort of like two separate entities, right? So they are not connected to each other in any way, and then don't see sort of inputs which are being fed by the evaluator into the other Gabble circuit. So we must ensure that the evaluator is not able to trick two different garbled circuits into accepting inconsistent messages. And the solution, again, uses these commitments that are published by the evaluator on the bulletin board. So specifically, we, in our CSAR release condition, we ensure that only the very first proof of publication that was published by some evaluator is accepted for round I-1. This ensures that, both the circuit for Brian and both the circuit for Ethan obtains only, a single set of the wire keys, which will correspond to Vipul's publishing message. Okay, and one other thing that is also related to this non-interactive issue is that we need to ensure that the garbled circuits are executed in the correct order. Meaning that if, someone wants to execute the garbled circuit of some honest party of round 5, then you can do so only after the garbled circuit of round 3 and 4 and so on have been executed. However, unfortunately, the evaluator again possesses all garbled circuits, and so he can do with them whatever he wants. And again, this is where we turn to the bulletin board commitments and designing clever CSAR release conditions. So we now ensure that the evaluator commits not only to the prior round, but in fact that the evaluator published commitments to all rounds before providing the garbled circuit of some round J. So effectively in our CSAR release condition, we check that proofs of publication have been published for rounds I smaller than J. Okay, and I guess the very final challenge is I have been saying that in this sort of clever encoding of the next message function, like it is fine to just give this encoding to the evaluator because it only leaks messages that are, published in the MPC protocol anyway. I have been lying, I guess, a little bit, because the next message function, in fact, also outputs this state, which in the original MPC protocol is assumed to be kept private. Right? And at the same time, this state is needed for the computation of the next message function for the next round. And there is no way to somehow pre-compute the state from the very beginning, because as you can see, it will also depend on the messages that are published by other parties. How do we solve this? We somehow need for the evaluator to be able to pass the state from one round to the next, but without seeing it, because this would disturb our security of the original MPC protocol. And the idea that we use here is that we slightly modify the original interactive MPC protocol in the sense that we encrypt the state under the party who is, governing this circuit, right? So under the party whose state it is, under the public key party. And the next message function is then outputting this encryption of the state instead of the state itself. And to be able to use it in the next round, we just use the hard-coded secret key of this party to first decrypt the state, and then we can just use the state as usual. Is this clear? Yeah. Okay, so maybe as a recap, in our main result, we were able to provide a transformation which takes any interactive multi-round MPC protocol, which is secure against fully malicious adversaries and is secure against T out of N malicious parties. And we transform it into a non-interactive protocol, which is also secure against fully malicious adversaries and up to T out of N contributors. But now we do not require interaction between the participants, and we only require a single round of participation from the contributors.
I have another question. With this, without the blockchain with polynomial simulation, the 4 rounds is the exact
Yeah.
round complexity. But I guess here you have a different model. There's like a
Yeah.
separation between data computer and battery.
Mhm.
So that lower bound, that 2 rounds of the lower bound also seems high as well.
Oh, so you're asking about related work, I guess. Sorry about that. We are exactly here. So there have been some work on the non-interactive MPC, which sort of have some different models. So something that is more similar to our work, in fact. But the model in the non-interactive MPC is that you have sort of a bunch of parties and you have a server, and the server is evaluating on behalf of these parties. So this is like similar, like the server is similar to our evaluator. And the difference is that, well, first of all, I guess we have sort of like one more round of like one more layer of separation, because in our construction, the contributors are not interacting with evaluators per se. But more importantly, in the non-interactive MPC, there is the issue that if the server, like if the evaluator is malicious, then the evaluator can execute the function f, where the honest inputs are fixed. But for the adversarial input, the choice can be like anything. So the adversary can get a bunch of results for the function f. And this is called this sort of like residual leakage. And this is inherent to this line of work.
I guess I'm asking about the 4 rounds lower bound.
For the 4 rounds, so I mean, it does not hold once you assume something like, you know, blockchain or something like that. No.
And what about in the plain model with only separating data computers and battery?
In the
Like,
plain
in
model.
the plain model, you count with 4 rounds, right? But now if you have data computer and evaluator, like now you have 2 round complexity.
I think it will also not hold there, but it will be still like a little bit different to our work. So I think like there you can achieve something like 2 rounds, I think.
2 rounds among data computer or among the evaluator?
I think for the evaluator.
2 rounds among the evaluator. How many in the plain model? How many rounds among data computer?
This I'm not sure, to be honest. But yeah, like it's like the 4 round does not hold it. It can be less than that. This is, I guess, the most important thing. But there are other issues. So like, for example, this like residual leakage issue comes up, and this is inherent. You cannot solve it unless you change the model a little bit. And this there is this other line of work which are called reusable non-interactive secure computation. And here what you have is typically you have 2 parties, and each party has some input, so X and Y. And the very first party somehow encodes this input and sends it to the other one. And then this other party can use this encoding to sort of compute multiple functions based on the 2 inputs, so based on X and based on Y. And then they can just send the result of the computation in one message to the first party. This is again slightly different from us in the sense that here the parties are actually still interacting with each other, and in our case we want to have a non-interactive solution, and the parties who are not interested in the output can leave after the first round. And finally, I guess there have been some recent works on MPC which sort of try to improve the flexibility of the MPC protocols. So in both Fluid MPC and YOSA, the parties who are not interested in the output can leave after the first round, but they like on the evaluator side, we assume that there is sort of a set of evaluators where in each set of the evaluators, at least half of them are honest. And in our constructions, we did not require that. So our constructions were secure even if all of the evaluators were dishonest, and like even if there was only one of them.
You also assume like a blockchain model. Fluid MPC is it also in the blockchain model?
I think Fluid MPC was something that was like similar to YOSO actually, if I remember correctly. But yeah, basically the idea there is that on the evaluator side, you're using committees which have honest majority. And that's pretty much it. That's all I have. Oh, sorry, future work, I guess, very briefly. It would be very cool to obtain a concretely efficient solution. This has been like a very theoretical work, and it would be nice to obtain something which is actually usable in practice. And finally, it would also be interesting to see if we somehow can make the encodings that we are storing reusable. So use them on some other allowed inputs or something like that. Yep. Thank you so much. If you have any questions, feel free.
A quick question, the thing about passing the state part.
Uh-huh.
So why don't you just like state instead of outputting the state in the clear, you output like the wires for the next garble circuit that you would want to feed in.
The wires to the next.
Like you put the wire labels for the state instead of
Wire labels for the
and then
state.
you don't retrieve those wire labels.
That's interesting. Yeah, maybe you can do that actually. Yeah, I'll need to think about it a little bit, but I think maybe this is fine. Oh. Yeah. Thanks so much, everyone.